everybody, it is I, your all-time favorite truthful educator. I'm here to get myself in trouble today. I want to talk to you about the truth behind science. They say that education is the art of lying without doing any real harm. And believe me, you've been lied to. I want to look at the laws of thermodynamics, but before you turn me off, here are just a couple things. First of all, you know thermodynamics. You may not know all the terms, you may not know the math, you may not know the equations, but you know thermodynamics. Science is experience-based. Now what we're going to talk about is going to sound very familiar to you because you are familiar with the laws of thermodynamics whether you know it or not. So don't be afraid. Yes, I'm going to throw equations at you because they are a very concise language. But don't worry about that. We're not going to go through a lot of complex mathematics. I'm just going to put them out there so I can explain them. The second thing I want you to know is that you've been lied to. When we present science, we present it like a gift. Here's this beautiful gift. Look at this beautiful package. And it has beautiful wrapping and little bows on it. And it looks complete and lovely. We don't show you the back of the package. We don't show you what we don't know. Everything seems like it fits together so nice and so neatly and so perfectly until you know the right questions to ask. And we never cover that. So I want to knock some weakness into those pillars of science that we have all come to love so much and rely upon. And you're going to discover that those pillars are not as strong as they look. And I'm doing this because I'm fascinated by it. I'm just fascinated. Now, does that mean I don't believe in them? No, I do believe in the laws of science. They are the best things that we have to date. But the laws of science, hypotheses, laws, theories, all of these things that are nothing more than an attempt to explain some collective observations that we have to date. Because science is observation-based. That's why these lectures are going to sound so familiar to you. Because you've been making these observations. You haven't been putting definitions to them, but you noticed them. So, I still believe in the laws of thermodynamics, but I'm fascinated by how weak they really are. Now, before we talk about thermodynamics, and we're going to talk about the beginning of thermodynamics. Let me try this in English. Thermodynamics. It's a little law that we like to call the Zeroth Law of Thermodynamics. Why the Zeroth Law? Well, somebody messed up. There we go. Somebody messed up. Somebody came up with the first law of thermodynamics, and everyone sort of said, oh yeah, that's where it all begins. And it was named the first law. It was agreed upon that it's the first law, and then someone came along and said, wait a minute. Before we have the first law, don't we need something more fundamental that explains this? This is more fundamental than the first law. But they didn't want to renumber the laws. Because if all of a sudden the first law became the second law, then people could be confused when you talk about the first law, whether you mean the original first law or the second law, and it's going to cause a lot of confusion, which if you knew what the second law of thermodynamics is, that confusion is actually, makes a lot of sense, but they didn't want to renumber them. But they wanted a law that had a lower number than 1, because that's how the laws of thermodynamics work. The most fundamental has a smaller number. And since we already had a first law, They called this the Zeroth Law. Now, before we talk about this, let's talk about the laws of thermodynamics. First of all, scientific laws do not apply universally. They only apply to the specific boundaries under which they were formulated. Okay? When we talk about the laws of thermodynamics, we are talking about equilibrium thermodynamics. These laws are the most generalized laws for us. These equilibrium thermodynamics laws are the laws that we live by most of the time. But they don't apply everywhere. Equilibrium means that these laws apply to very slow, gentle processes, like eating and breathing. These are slow, gentle processes. And these laws apply to anything, not just in chemistry, not just in physics. I'm talking everyday life must follow these laws if it's a gentle process. For example, have you ever been in love? Because love can only occur if they follow the laws of thermodynamics. Everything follows the laws of thermodynamics. Now, the poets out there watching this are going to argue with me. The philosophers. How can something abstract like love follow strict chemical and physical laws? Well, love, with my apologies to my poet and my philosopher friends, I don't have any because they used to debate whether or not the universe exists. But in my lab, I had a bottle of universal indicators, so I know the universe existed. But with my apologies to my friends who are free to argue this, the one thing about science, disagreements occur. But when you fall in love, what's happening? There are chemical processes in your brain. There are chemicals that are released, the same chemicals that are released when you eat chocolate, as a matter of fact. Chocolate is also a depressant, and I do not think that's a coincidence. Anyway, chemicals are released. There are neurons that are fired off using electrical impulses and things of that nature. Those chemicals, those electrical impulses, all follow the laws of thermodynamics. So when I say everything has to follow the laws of thermodynamics, I mean yes, everything. Within the scope of the laws of thermodynamics. What do I mean by the scope? Well, if there's an equilibrium thermodynamics, that implies that there must be a non-equilibrium thermodynamics, as delineated in this book. This is my light reading for the summer. Non-equilibrium thermodynamics applies to particularly violent processes. Processes where there's a lot of motion of molecules of matter, a lot of sudden, like explosions. Explosions are so violent they really don't follow the laws of equilibrium thermodynamics. They do follow the laws of non-equilibrium thermodynamics. Scale matters. My degree here is in statistical thermodynamics. Statistical thermodynamics is the bridge between classical thermodynamics, equilibrium thermodynamics, and quantum theory. As it turns out, if you get to systems that are too small, classical thermodynamics breaks down. That's why we needed a second set of laws, quantum mechanics, to explain behavior that we cannot understand because we follow the classical laws of thermodynamics. The quantum laws of thermodynamics make no sense to us at all. We can understand the lessons that quantum mechanics is teaching us, but that's a far cry from actually understanding the laws of thermodynamics, the laws of quantum mechanics. I suspect that the laws of thermodynamics also breaks down on a particularly large scale, a cosmic scale. I think this is why we're having trouble with the standard model in physics right now. I believe that if you start talking about a system that's too large, other effects that we are not considering will come into play, such as perhaps Einstein's curvature of space might be wreaking havoc on the standard model. Or maybe we're still expanding from still accelerating from the Big Bang. If there's an explosion, everything begins with an acceleration. And that acceleration will continue for a certain period of time until an equilibrium velocity is reached. We've seen this. You've seen this. So maybe we're still just too close to the Big Bang for the standard model. I don't believe in dark matter and dark energy. To me, you can't just make up things to explain what you can't understand. You have to come up with a better explanation than that. And yes, I have physics friends who are going to argue this, and you're allowed to. It's okay. But every day there are more hypotheses coming out to explain what dark matter explains without relying on dark matter. Here's the thing. Science has a long history of making up particles that have always proven to be wrong. Every single time. Phlogiston. The Greeks proposed an ether. The ether was the invisible stuff that encompasses the entire cosmos. Well, guess what? That sounds a lot like dark matter to me. Phlogiston was what was holding molecules together before we understood the laws of bonding and non-bonding forces. Polywater was popular in the 60s to explain certain phenomena that they couldn't explain. So it's not so much that I don't believe in dark matter, I don't believe in making up things. Maybe, just maybe, that's why they've never actually been able to prove dark matter. But that's well beyond the scope of our discussion today. So when I tell you that I'm going to discuss the truth behind science, this particular law, the Zeroth Law, there's not going to be a lot that's controversial about it. But I already just gave you stuff that's controversial. Whether or not we can believe the laws, you know, I once proctored an exam at a university where I was teaching, and for some reason they made me the proctor of all of our computer science majors. Many of whom I knew, because many of them took my courses as a general education science course. I was kind of goofing around with them, saying, hey, you know, you all should be chemistry majors. I don't know why you're over here in computer science, yada yada. Well, I was joking. By the time they take these exams, they're too far into their major to really want to change. They know what they want, and I know that, and I respect that. I was just kind of having some fun. One of them actually made the comment to me. He said, the reason we like computer science and not chemistry is because everything is known in chemistry. We know everything, but in computer science, you never know how anything is going to work. Well, I looked at him. I said, you realize you have that just backwards, don't you? The only thing we know in science is what we don't know, which is a lot. But if you don't know what a computer program is going to do, that's because you're working on an IBM. Anyway, I'm going to get sued. Anyway, so here's the Zeroth Law of Thermodynamics. Let's walk through it. Now, with every law, I'm going to introduce terminology and an equation. One of the terminologies I want to introduce today is called the system. The system is a region of interest. It's a region of space. It's what it is that we are discussing at the moment. I don't have my bottled water with me, or I'd pick it up right now. And I would be saying to you, for example, we can talk about this bottle of water. That becomes the system, because that's what we are discussing. That's the system. Everything that is not in the system are called the surrounding. Now the surroundings are important because sometimes we have exchanges between the system and the surroundings. If my cup is open, water molecules can evaporate up into the air, dust can get into the water. So there's a flow of matter between the system and the surroundings, plus there's a flow of energy as well. So sometimes the surroundings are going to be important, sometimes they're not. A lot of times we're going to isolate our system so there are none of these flows, and we're allowed to do that because we're talking theoretically. We're not talking actual systems. We're saying here's an ideal system. And making it ideal means we can make unrealistic assumptions about it just to get concepts through. If you add your systems to the surroundings, you get the universe. The universe is everything from that cup of water to the room, to my house, to the city, to the country, to Pluto, to Alpha Centauri. Everything is in the universe. Everything. So let's talk about a system. Suppose we have a system isolated from the surroundings. There are two parts to the system. We have the left and the right side. Now it's closed, so we're not going to exchange matter, and we're going to insulate it. So here we have a perfect insulation. We can approximate this as styrofoam, for example. Now styrofoam is not a perfect insulator. So it's an approximation to an insulator, but we're talking about a perfect insulator here. No matter is being exchanged with the surroundings. No energy is being exchanged with the surroundings, which means the total energy of these two sides is fixed. But, and this is a big hairy but, let's assume that they are not at the same temperature. So we have a temperature of the right side and the temperature of the left side. Did I label that correctly? I think I did. I don't know. What do I know? And just for argument's sake, let's assume, and this is arbitrary, I could just as easily choose it the other way, but let's assume that the left side is greater than the right side. So the temperature on the left side is higher than the temperature on the right side. These two systems are not exchanging matter, but they are in thermal contact. In other words, suppose we have two coins stacked one on top of the other, only sideways. Here I drew it sideways, so it'll be sideways. We have two pieces of metal, insulated, different temperatures. Higher temperature on the left. Here's what the Zeroth Law says. Two bodies in thermal contact will exchange something until the temperatures are equal. Early thermodynamicists did not know what this something was. They said something has to be flowing from the high temperature to the low temperature. They did not know what that was, so they called it heat. And they gave it the symbol Q. We gave it the symbol Q. Why Q? I honestly don't know. I always assumed that Q was sort of short for quantity. Quantity of something that they're going to call heat. Quantity of heat is transferred until the two temperatures are equal. So the higher temperature body, as it loses heat, will begin dropping in temperature. The lower temperature body, as it gains heat, will begin raising until the two temperatures are equal. You have seen this. If you've ever put your hand on a hot stove, you felt it as heat flowed from the stove into your hand. If you've ever had a glass of ice water, you've recognized this as well. Because the ice is lower temperature than the water, heat flows from the water into the ice until the ice melts completely, and then they're at the same temperature. Now it's a little different because in your glass of water you're also exchanging heat with the surroundings. It's not insulated, but we try, don't we? We get those tumblers and we try to insulate it, and if it's a good tumbler, it can hold that temperature for a long time. But eventually that heat flow will cause the two temperatures to be the same at some point. We've also been throwing around the term temperature without having defined it, haven't we? That's an oversight. But now that we know what heat is, and by the way, heat always flows, by definition, heat flows from a region of high temperature to a region of low temperature. Temperature now. Temperature is simply a measure of quantity of heat. The higher the temperature, the greater the heat. That's why it's actually improper on a hot day to say, ooh, it's hot temperatures today. No, a temperature is a measure. It can't be hot or cold. It's just a number. But higher temperatures do indicate higher quantities of heat in the surroundings. So temperature is a measure of quantity of heat. Nowadays, we know what heat actually is. Heat is related to the kinetic energy of the substance. Kinetic energy is how fast the atoms and the molecules are moving. The higher the temperature, the faster those molecules move. At lower temperature, they slow down. This is why there has to be a minimum temperature. You've heard the term absolute zero. And you've heard it even when not talking about my ex-wife. Absolute zero is the coldest temperature possible. Most people know in Celsius it is negative 273.15 degrees Celsius. A lot of people forget the 0.15 because most teachers just leave it off. It's actually 273.15, and even that's truncating it. There's more digits after that. The absolute temperature scale in Celsius is Kelvin. The absolute temperature scale in Fahrenheit is called Rankine. Celsius is not the only temperature scale to have an absolute zero. Fahrenheit has it as well. And if I'm remembering correctly, and I'm probably not, so don't quote me on this. Look it up if you really want to know. I'm thinking it's around 460 degrees below zero Fahrenheit. I think. Don't quote me. Now there should be a way to relate heat to temperature. Well, we're not really going to relate absolute heat to temperature. Let's relate changes in heat, and you're going to see this symbol a lot. This is the capital Greek letter delta. Looks like a triangle. And it means change in. And by definition, it is always final minus initial. Final minus initial. So if we want to know our change in heat for our system, we can call it the left side, we can call it the right side, doesn't matter. The change in heat, ooh, hope you didn't hear that. I tried to sneak one out there, but Lord, it had a voice of its own. I apologize for that. Whew, little thermodynamics going on there too. Anyway, change in heat. And you know this so well. First of all, the more matter you have, the more heat it can hold. You know this. If you're trying to heat up a nickel, it's going to take a lot less heat than if you're trying to heat up an automobile. So mass is a factor. So M is mass. And change in heat is going to be related to the change in temperature. Notice I left a little space here. So if we measure the change in temperature, we can actually measure the change in heat. What's missing here is called heat capacity. First of all, I need to get this off my chest. If you are a science teacher and you use the phrase specific heat capacity, or if you are an author who has ever written specific heat capacity, shame on you. There is no such thing. It is complete nonsense. Somebody somewhere did not understand the difference between specific heat and heat capacity, and they just jammed them together, and they published a book saying specific heat capacity. Here's the difference. If you went through graduate school in chemistry and you never bothered to learn the difference, that's on you. Shame on you. If you are a student sitting in a chemistry class and you're watching this video and you hear your teacher use the term specific heat capacity, don't call them out. But know with a subtle satisfaction that you are smarter than your chemistry professor. But don't say anything, because you know you want a passing grade, and to get a passing grade you have to parrot whatever an idiot teacher tells you. Here's the thing. Heat capacity, by definition, heat capacity is the amount of heat required to raise 1 gram of water 1 degree Celsius. This is where the term calorie came from. Calorie is a measure of heat. And the heat capacity for water is 1 calorie per gram degree Celsius. Or Kelvin if you prefer, because you're taking a difference in temperature. So it doesn't matter if it's a Kelvin scale or a Celsius scale. They'll both give you the same change in temperature. This is the definition of a calorie. Now be a little careful, because a nutritional calorie is a different thing. If you're talking nutritional calories are written with a capital C, as opposed to chemical calories written with a lowercase c. I hate that convention, because it's hard to talk about it without showing it. A nutritional calorie is actually 1 kilocalorie. A nutritional calorie is the amount of heat required to raise 1,000 grams of water, 1 degree Celsius. Okay? So a nutritional calorie is simply 1 kilocalorie. Now, the calorie of, specific heat of a substance. If you have a metal, and by the way, all heat capacity is, it's the amount of energy required to raise the temperature of 1 gram of material 1 degree Celsius. You're familiar with this too. Some things, it takes much less heat to raise the temperature. And some things, it takes much more heat. For example, boiling water, burned myself on, I was trying to make some ramen noodles. And I had a pot and I had water in it. I was trying to boil it. And I touched the edge of the pot and I burned myself even before the water started to boil. Well, metals have a very small heat capacity. It takes very little heat to get them to raise temperature. And that pot's temperature had risen quite high. The water inside has a much larger heat capacity. One is fairly large. So in the same amount of time, being applied the same quantity of heat, or we'll assume it is, that water temperature did not raise quite as much, nearly as much as the pot did, because the pot has a much lower heat capacity. The handle, that plastic handle, that heat capacity is huge. It takes a lot of heat to raise that temperature of the handle up. That's why it's an insulator. That's why they put the handle on there, because you have to apply a lot of heat to force that temperature to increase. So, you're familiar with heat capacity. Some things heat up faster than others. That's all heat capacity is, a measure of how fast something heats up. So suppose you have a metal with a heat capacity of 0.26 calorie per gram degree Celsius. That's the heat capacity of our metal. 0.26 calories per gram degree Celsius. Specific heat, on the other hand. And pay attention, teachers, this is what specific heat is. The specific heat of a material is the heat capacity of that material divided by the heat capacity of water. Oops, sorry. That is specific heat. It's a relative heat capacity. It is relative to the heat capacity of water. So what is 0.26 divided by 1? It's 0.26. So what's the difference? The units cancel. Specific heat is a unitless number. So what is specific heat capacity? It is a unitless number with units. It makes no sense. Stop using this expression. A lot of times, books nowadays will give you a specific heat capacity, and they'll give you joules per gram degree Celsius. Well, guess what? If you're giving units, it's heat capacity. It's not specific heat. And if you want to convert these numbers to joules, it doesn't matter. The specific heat will be exactly the same, because to convert it to joules, you have to multiply it by a constant, 4.184 if I'm remembering correctly, which I may not be. Well, if you multiply both of these by 4.184, that's going to cancel. The specific heat is always in calories per gram degree Celsius. But if you're giving joules, or if you're giving calories, if you're giving units at all, that's heat capacity. That's not specific heat. Okay, that's enough of that. Getting off my soapbox. I hope I pissed some of you off, because if you are pissed off, you probably need to be. If you trusted the author of a textbook that you learned from, you're allowed to be angry at that author, because I'm angry at that author. They don't know what they're talking about. And the publishing company should be equally ashamed. We're the editors for these science books. I'm for hire if you are in a publishing company. Okay, anyway, back to the point. There's two ways we can measure heat capacity, by the way. To do it formally correctly, it has to be measured. You have two ways to do it. Okay, most of the time in chemistry we measure heat capacity at a constant pressure, which means we have a beaker that's open to the atmosphere so the pressure does not change. But if you have, let's say, a pressure cooker, now the volume does not change, but the pressure does. So a lot of times you should, actually, if they're doing it correctly, you will see, not C here, you will see CP. That CP means that is the heat capacity at a constant pressure. Again, aside from the fact that I explained to you that the laws of thermodynamics only applies to a narrow range of situations, slow processes, not too small, and probably not too large, there's not a lot here. There's not a lot to argue about, because you know if you have two bodies in contact at different temperatures, eventually they're going to reach an equilibrium, where there's equilibrium by definition, no observable change over time. So eventually they'll reach the same temperature and it doesn't look like anything is happening there at equilibrium. You know this, you've seen this. You know that some things heat up faster than others. I learned that again trying to make my ramen noodles. Boy, did that hurt. And the change of heat is related to the mass. Well, you know that too. You know it's easier to heat up a coin than it is a car. And that's all the zeroth law is. The laws of science, no matter what laws you're talking about, science is experience-based. Okay? You can go and you can design an experiment yourself, doing something like this, if that's what you want. And this is how science works. Someone makes an observation and they come up with a hypothesis and they say, hey, you know what? I think that we're exchanging heat relative to the amount of material, what the material is, and the change in temperature. Then they went out and they created more experiments to test that hypothesis. And that hypothesis always proved true. Then other people went out and said, now wait a minute. And they set up experiments to test that hypothesis. And that experiment, those experiments, always proved true. Does that mean that this law of thermodynamics is true? No. That means we have never been able to prove this law of thermodynamics is wrong. Does that mean it's wrong? No. As time goes on and we test it more and more, the likelihood of this law being wrong becomes smaller and smaller and smaller. And at this point, I just don't believe that we'll ever find anything to disprove this law. So I accept it. And one of the more important things about these laws is it helps us to make predictions. And we can make a lot of predictions with the zeroth law. You can make those predictions now as well. But an interesting fact about science. First of all, there are no facts. Everything is up for grabs. Nothing can ever be proven as accurate. Nothing can ever be proven as true. The best we can do is prove something is wrong. We can prove a hypothesis wrong. Sir Isaac Newton proved that the hypothesis that heavier bodies fall faster than smaller bodies, he proved that was wrong. Nobody has ever proved Newton's law is correct. We test them. We test them and we test them and we test them and we test them, but they can never be proved true. And someday somebody, some particularly brilliant young person, maybe you, will find that one exception that proves these laws wrong. Would that be a bad thing? Nah. Because if you prove these laws are wrong, guess what? We get to start all over again. What an exciting time that would be. Now be a little careful. Because like I say, scale matters. And if you prove that these laws fail at super small scales, well, someone's already beaten you to it and they've already found a way around it. Statistical thermodynamics, by the way, what I do, that's the bridge. You get a lot of these really small subatomic particles, get enough of them all acting together, their behavior, strange as they are as individuals, have to add up to the classical laws that we know. That's the goal of statistical thermodynamicists, to see how quantum laws add up to classical laws. It's the bridge between the two, and yes, it's been done. I have 3 more laws to go. This is just the first one. We're not going to cover it tonight. And the reason we're not going to cover it tonight is because I am out of here as soon as I can find the button.